Hi, in this video we will go through the properties of matrix multiplication. Well, the first fact about the matrix multiplication is that the matrix multiplication, let me write it, multiplication is not commutative. What does it mean? It means that, well, if you have two matrices and you can multiply A to B, first of all, there is no reason that you can multiply B to A from the left. And even you can multiply and you get it is defined, then there is no reason that these two are going to be same thing. Okay. Well, this non-commutativity has different levels. So let me just go through the first thing. For example, if A is 1 by 3 and B is 3 by, say, 2, then we can multiply A to B, and AB is going to be a matrix of dimensions 1 by 2. But BA is not defined. And well, then it just shows that you cannot change the order of multiplication in matrices that easily. Well, this is the first level. Well, A is 1 by 3 and say B is, let's say A is 2 by 3 and B is 3 by 2, then yes, you can multiply A to B, and AB is going to be 2 by 2 matrix, and you can multiply B to A also, and this one is going to be 3 by 3 matrix. It is defined and it's 3 by 3 matrix, and there is no reason, well, obviously this cannot be equal to 2 by 2 matrix. This is another level. AB is defined, BA is defined, but AB does not have the same dimensions as BA. But the problem is even deeper, and that's actually where this non-commutativity becomes important. So let A and B be square matrices of the same dimension. Then, well, obviously you can multiply A to B and B to A, and they're going to have the same dimensions. But this doesn't stop here. Still, you can have AB and BA both defined having same dimension, but the result may not be equal. For example, this is a very interesting, it will be very interesting practice. Try to generate two matrices when you multiply from left A to B and from right A to B, then you don't get the same thing. So let me just give you one nice example. This is A, and then B is, say, this one. And now you see, if I multiply A to B, this will give us 0, 1, 1, 0, and this gives us what? 0, then 1, then 0, and then 0. How about BA? BA is 0, 1, 1, 0, 1, 0, 0, 0, and this gives us, well, the first one is 0, the second one in the first row is 0, then this is 1, and this is 0. And you can see that obviously AB is not equal to BA. And this gives us the source of why matrix multiplication becomes important in something like quantum uh, mechanics. And this is source of lots of new things and nice things. So while I encourage you at this stage, you stop and try to find pairs of matrices which don't commute. Means that if you multiply a to b from left, it won't be equal to you multiply b to a from left. Okay, so that's the first thing in the list of the important facts knowing about the matrix multiplication. But then the properties come in. So what are the properties that are nice here? The first property is that, well, this is associative. The matrix multiplication is associative. So it means that if you want to multiply three matrices, you can put two orders here. Both of them will be the same thing. And well, this is just like number multiplication also has this property, yes. And here I'm picking A, B, C such that the product is defined. When it is defined in one form, in other form will be defined, and this is what it comes. The second property is that, well, matrix multiplication and matrix sum addition work nicely. So it means that we can expand, but while expanding you have to always be careful and keep the order as it is. You see, a is multiplied from the left, so you multiply a to b from left and a to c from left. If this is from the right, so if you have from the right, then you multiply c from the right to a and b from the right to b. Sorry, c from the right to b. Yeah. So these properties are called distributivity. And well, you can see this easily how to prove this thing. For example, let me show the left distributivity, which, so if I want to find the entries, let me just write ij entry of this. You know that in ij entry of the product is that row I of A, you dot product with column J of B plus C. But column J is the same as you have column J of B added to column J of C, and we know that dot product and sum of vectors work nicely together. There's a distributive, so we have column J of B plus row, this is row I dot column J of C, and you see row I dot product column J of B, it is same thing as entry ij of AB plus, well, this was A again here. This is the second one is ij entry of AC, and then this is same thing as you have AB plus AC, you added ij entries of those ones, and you can do the other one also yourself. The important thing is, again, is that when you're distributing, you should be very careful about the order. In other words, you cannot just write a B plus C equals to BA plus AC. This is not true in general. Okay. So those two properties, distributivity, and then, well, also we studied the relation between matrix addition and multiplication. Also, you can do matrix multiplication and scalar multiplication. Yes, k is a scalar. This will be the same thing as you multiply ka first, then multiply to b. Also, you can do the other way around. Also, this is what you can do here. Well, to see that, this is not very difficult to see. K, A, B, I, J entry is, well, you know that the scalar multiplication works component-wise, means that you have I, J entry of A, B, and then multiply it by K, and this is K times row I of A dot product column J of B. And we know that the dot product and K scalar multiplication work nicely together. It means that we can first multiply this guy, scalar multiply K to I row of A, and then dot product it by J columns of B. And this is same thing as row I of K multiplied to A. And this means that, well, ith row of Ka multiplied to jth column of B. This means that we have Ka multiplied to B entry I J. And one last thing is that the identity matrix works very as 1 for the matrix multiplication. So if A is square matrix, then we have A times I. It is same thing as I times A. I is identity matrix. Remember, IN is the main diagonal is 1. Everything else is 0. So these guys are good. They from multiply from left from right, you get the same result. You get A. And if A is not a square matrix, it's just a M by N matrix, then we can multiply A from the left by identity matrix of order M, and you can multiply from the right by identity matrix of order N. Both of them are going to be the matrix A. So this means that identity matrix, especially this one is the one I like more. Identity matrix is like 1 for the matrix multiplication. Remember, you multiply 1 to any number you like, you will get that number back. Also, it means another thing. Note that the property just we have, this implies that identity matrix commutes with all square matrices of order n. So you multiply from left or from right, you get the matrix A back. So that means that you change the order of the multiplication, and that is the same thing. Okay, so these properties specifically get interesting when you try to check the identity. So let us see example. So when you try to check identities, something like well, remember in the numbers case, if you have A plus b squared. This is same thing as a squared plus 2ab plus b squared. How about matrices? How about matrices? So is that true that a plus b squared equals to a squared plus 2ab plus b squared? Is that true? Well, let's see. A plus b squared means what? Means that we multiply ab to itself. And this means what? This means that, well, we can expand this from the left, and from the left for this we get a times a plus b first plus b times a plus b. This is distributivity from the right, and then you do another time here, you get a times a plus a times b plus b times a plus b times b. But we know that a times a is same thing as a squared, and b times b is b squared. Here in the middle we have ab plus ba. We know that in general ab is not equal to ba, so we cannot just switch the order of this guy and write this guy as ba, ab, and then get the result. So this is not true always. You cannot change the order. But let's say that this a plus b squared, which we found is a squared plus ab plus ba plus b squared, let's say these guys are equal to this. Then we can subtract both sides from a squared, so these two cancel. From b squared, these two cancel. ab plus ba equals to 2ab. Then that means that, well, I can take this one to the other side or subtract both sides, minus ab. Then we get ba is equal to ab. What does this mean? This means that, well, first of all, in general case, this is the best result we can get. Okay, but if this is true, that will imply that a b is equal to ba. Means that a and b commute. And this will be true if and only if. So a plus b squared will be equal to a squared plus 2ab plus b squared if and only if ab is equal to ba. So if someone wants to find a counterexample for this equality, you just need to go up there, the example that we had for these guys. You will see if you do a plus b then square, you will see that it will be different than a squared plus 2ab plus b squared, because these don't commute. So that's, so in general the identities, you have to be careful and you have to do step by step and see if that the identities hold or not. Okay, so these were the list of properties of matrix multiplication, and we saw some nice examples.